Now, we've just been through quite a lot of work. We're at quite some pains to determine the charge on our capacitor as a function of time t. Let's now step back a little bit and try to analyze our results here. Look at the various limiting cases and behaviors. Well, moving up then to our next page here. I'll keep this one, though, here in view. If I were to make a plot of this behavior, I would be plotting then as a function of time t, the charge on my capacitor, Q of t. And the first interesting limiting case is at time t equals 0. If I substitute in 0 for t, I will get e to the power 0, but we know e to the power 0 is just 1, so I get 1 times q naught. So I've just learned that when t equals 0, here near the y-axis, the value of q will be q naught. So indeed, our solution respects what is known as our boundary condition that we started at q naught. As time t goes to infinity, then I'll have e to the minus infinity, which is clearly 0, and so the charge then is going to be approaching 0 at long times. So we have this kind of an asymptote. And that is more or less what we were hoping or expecting, because after all, we've just taken this capacitor with his plus and minus plates and allowed the charges to leave the top plate and go to the minus plate by flowing through the circuit. And so eventually we expect ourselves to end up with 0 charge. In between, what we have is this nice exponentially decaying function, which then, generally speaking, is going to look something like this. And the last interesting quantity that we have here is this ratio here, R times C. It's a nice little fact about exponentially decaying functions. If I were to look at the slope of my curve at the origin, and just imagine that the change in time of this charge stayed constant. It doesn't, but if it did stay constant, the charge would follow a path somewhat like I've just sketched here. And there's a particular point in time where we would hit the origin. And that point in time is actually this product, R times C. We know that because of an interesting fact about exponential functions, and that is that, well, if you have any exponential function that follows the form e, some prefactor times e to the minus time t divided by tau. Tau is called the time constant. This time constant, tau, which in our case equals R times C, then that point of intersection with the axis will occur when you reach one time constant, or 1 tau, like so. Very good. So that then tells us basically the time scale it takes for this decay to happen. The time constant, this tau, has a name. It's called the RC time constant. It's one of those nice things where the name for the thing is actually the formula, so it's not too hard to memorize. Okay, so now we see how the charge has been behaves with time, but that's not actually what we had set out to do. We actually had wanted to determine the current, I, as a function of time t. We were interested in that because we wanted to compute actually the power dissipated here in the resistor. So let's now take a look at that current I of t. You will recall that we had determined that the other terminal relation for our capacitor, given the sign conventions that we've established, was that this current I of t is equal to minus the time derivative of q. Fortunately, we have a nice formula for q, so we can carry out this time derivative. So this will be equal to minus the time derivative, d by dt, of our function for q of t, which is q naught times e to the power minus t divided by r times c. And when I take this derivative, what we find is that, well, my constant q naught comes out. When I take the derivative of the exponent, I'll get my exponent back again, but then times whatever is multiplying t. So there will be a factor of minus 1 over RC. But there's also a minus sign here on the outside. So when I put this all together, I will get minus Q naught, right? That's what I have out in front that I've pulled out. Then the minus 1 over RC, so that'll be divided by minus RC on the bottom. And then I will get my exponent e to the minus t divided by RC. Here, notice the minus signs cancel out very nicely. So now I have an interesting formula for the current. This, I think, is a result which is also worthy of making a nice sketch. So let's make a sketch for the current as a function of time t. So that will look something like this again. Here's time t. This is the current at time t. Once again, we have our classic exponential decaying behavior. As time gets very long, the current is going to drop off exponentially. It begins at time t equals 0 at a particular value equal to Q naught divided by RC. And then it decays exponentially. And like before, if I take the initial tangent line and project it downward, this intersection point will be tau, which will equal whatever t is being divided by. Again, that's this quantity r times c, which we've identified as tau. So tau, that intersection point there, will be r times c. Very good. So there's a couple of interesting lessons here, actually, that are important to keep in mind, very useful when analyzing these type of capacitor circuits. A favorite type of question to be asked on exams and so forth, and also important to know in general, is to be able to answer the question of, well, when I have a capacitor like this that starts off with a charge Q naught, it's good if we can have a quick way of determining what the initial current will be flowing through that circuit, and also what the current will be after long times. Now, those two results are actually evident in the particular result that I found here for the current I as a function of time t. So let's take a look. You notice the initial current. The initial current occurs when I've got my capacitor charged up, right? He has a charge Q naught on him, and he's wired up to this resistor. And what I'd like you to notice is that as we go to small times, as t equals 0, this capacitor, look at its symbol. It actually looks a lot like a battery, right? It's carrying a certain charge on it, and it also has a certain voltage associated with it. From our basic terminal relationships, we know that the voltage going from the minus to the plus side of the capacitor is always equal to the initial charge divided by the capacitance. If we think of this thing then as a battery, it acts initially like a battery of this given voltage. And then as the charge begins to flow off, quickly, okay, fine, the current begins to drop. But initially, the current should be just what we would expect given that voltage. It looks like a battery for the first few instants in time. So if it were a battery, I would expect that the initial current would be the voltage, right? The initial voltage divided by the resistance. And in fact, that's just the formula we found, because our voltage was Q on C. Now it's the voltage divided by another factor, R, so it's Q naught over RC. And that is, in fact, exactly what we found for the initial current. So the first lesson is that as t goes to 0, the capacitor acts like a battery with the EMF equal to the initial charge divided by the capacitance. The next limit to consider for such a circuit is what happens as t goes to infinity. Now, as t goes to infinity, what you'll notice is happening is no more current is flowing through my capacitor anymore. I've reached an equilibrium state where everything has settled down. And in my capacitor, when everything has settled down, there's no more flow through the capacitor. And the capacitor is acting very much just like what it looks like. What does the capacitor look like? It looks like a broken circuit. There's no actual connection between the plates. So as t goes to infinity, the capacitor acts like a broken wire or a broken circuit, a broken wire. And in that case, we find, of course, that the current going through it then is going to go to 0, and that is, in fact, precisely what we found through the solution of our differential equation.